So this is the special class on magnetic properties of material, and there are several other videos are uploaded in my channel related to that optical related to magnetic properties of material. And one thing that is whatever we have included in so for the magnetic properties analysis, what in general we perform generally, that is that spin polarization term. And, when we include this spin polarization term in structure input file, and this creates a spin up and spin down columns in das bands. And second, that the magnetic moment in the result file and output file. So this is that simple method of analysis of magnetic properties of things, and we can just report this magnetic moment of any material. And also sometimes we can calculate that magnetization energy by using that non-magnetic and that before that is spin polarization and after spin polarization energy, we just take the difference in the energy, total energy, and we get this magnetization energy. So this was that earlier exercise we have performed. Today I am covering this one is this spin polarization along with this spin polarization. This non-collinear effect, non-collinear effect, uh, a non-collinear polarization effect I'm going to include in this part. And here we will have this spin vector, and this is some sort of spin orbit coupling, although there is some difference in spin orbit coupling and this non-collinear effect. So let me show you that the answer given by this chat gpt, that in the non-collinear spin polarization, in non-collinear spin polarization refers to the situation where the spin of electrons are not aligned in a parallel or interior parallel manner, and the spin has a different orientation with respect to each other. It can occur, for example, in materials with magnetic impurities on in certain magnetic structure where the spin direction varies spatially. In non-collinear, spin polarization is very important in spintronic devices. In spintronic orbit coupling, it's actually that relativistic quantum mechanical interaction between electron spin and orbital motion around that atomic nucleus, and this gives their own effect. But similarly, there is not much difference. But yeah, this is that non-collinear spin polarization is actually that the orientation of electron is spin related to each other, where that spin orbit coupling describe the interaction between the electron spin and the orbital motion. So these are the different. So let's start uh, how we perform this exercise in the material. And one of the example I am taking here is that one structure, that is TIZRN, where this this is that structure I'm having, and here, so that Ti and ZRN are 50-50. So this is where that label. Let me show you the symbol. So these are that ZRN. So in TIN, 50% Ti atoms are replaced by ZR, and this system is now TIZRN system, and this is zigzag nano ribbon. So we are trying to observe that non-collinear uh, magnetic properties of this particular nano ribbon. So what is the that modification we have performed in FDF file. Let me show you. So here this is that system level and other things are same. This is that coordinates, and one thing that is uh, included here is these two lines, that is spin polarization true. So this is spin polarization true. This is the this is that this is for that spin this can be also used in ordinary spin or magnetic properties motion. Second one is that is here this is spin non-collinear. This is that additional terms we have added, and uh, and one more thing that I want to include here, that pseudo potential file that is included is that non-relativistic pseudo potential we have used here. So these are uh, that non-relativistic pseudo potential. So before running this, we have to create this that relativistic pseudo potential of this Z, R, and Ti, and whatever that component is species, and run Siesta, and this is that output file. So in this output file, so other things are same. These are the things, and at the end, this total cell volume and other parameters are given, as well as this is spin moment. This is the total spin moment along the other direction is sorry, total spin moment along x-axis. This is given. So and apart from this, if we want to go to that DOS file, so in ordinary spin polarized statement, when we create this dot file by using eig2 DOS, then there will be two more columns here. One is that for spin up, and second one is for spin down, and we create that spin up and spin down plot, like let me show you. Earlier we have performed like this. So this is that yeah, this is that uh, upper plot, and lower that is spin up, and this one is spin down, and we can have this uh, magnetic property. So let me compare this output file and input file. So here in this case, that input file is where is that input file. So here that input file is fractional, and here also that non-collinear I have shown. It's a different file, and for this MN. So I have tested this for non-collinear terms. So I should have some file magnetic moment. So I have tested that for that non-collinear. So that file is not available here. What actually I wanted to show you. So after that, I have checked this for non-collinear. So this is the same file, anyways. Okay. Okay. So let me show you what we have to do for this. So let me go to that result file. So here that result file is this is that result file. All the parts are here, and let me go to the end of this to get relaxed. So these are that relaxed coordinate, and before that, these are that distribution of orbital charges, spin, and one thing is this SVEC. This is spin vector, and in order to plot that spin vector, we need this data. So the question is how we will use this data. This is that the distribution according to different orbital suborbitals, and the total spin vector, it is given in the last part of this is the total of one particular elements, and there are total 40 atoms in this structure, and out of this 40 atoms, these are that 40 atoms, and the 20 atoms will be of nitrogen, and 10 atoms of titanium, and 10 atoms of that zirconium Zr. So we have total 40 such atoms here listed here, and sorry, this is let me close this here. So this is 1 3 5 7 up to 40 atoms. So we have to use this data. So let us start working on non-collinear magnetic plotting. So first of all, we have to use that step number one is we have to create one XSF file from this XV file. So where is that XV file available? So here, that is yeah, this one is that XV file, and we have to create that XSF file as the first step. So in order to create this, we have one tool, that is XV2 XSF. This is that file we will use to create XSF. So we have to give that PIZRN underscore ZNR. So this is that file name, system label. So okay, so this will create that XSF file. So this is that created XSF, and then let us open this XSF file here. So here, so this is that XSF file. So generally, if you want to display this XSF file by using X Christian, so that is X Christian, the XSF star dot XSF. So this is that file, that is structure of that nano ribbon, zigzag nano ribbon. So we have to modify this XSF file, and what is that modification? Let us see. So we have to club this data with that data available in this population, atomic and orbital population, molecular atomic and orbital population, especially this part, spin vector part. So this data we have to merge, and not all the one, but this last one. Yeah. So again, obviously, we need to do all these manually, and let us use that Excel. So let me copy this and go to Excel sheet. So let me clear new. What is happening? So new Excel spreadsheet, and here let me paste this, so that these files are, let me align the columns. So here these are that standard column. Okay, so this is the term, so I can delete this. And let me number this from 1 2 3 4, and oh sorry, it's from this one. Let me start from this, and go to this. So there are 40 atoms, yes, good. And also I can start this to 3 to 4 digits. So let me format this as yeah, it's now looking like good. So we have to paste here that in the right hand 3 columns of that spin vector. So this is that initial one, data available. The next one, let me work on second data, that is from this result file. And here let me start from this atom to the last one, up to 40, that three elements. This is for the titanium, zirconium. For all three elements we have to copy this. Yeah, so up to this relaxed atom, let me copy and paste in the Excel sheet and start working. So yes, so again the first column is important for us, and others are mandatory, not mandatory, but these last three columns, these are very important because we have to use these three data. So three columns uh, should be here less. So that last one, this is, so 111, and the last one is that total. Remember this. So let me delete other parameters, and we have to keep these three. So let me delete this, and also I can delete this one. So the last one is the total one. So this one is important for us, and second is, now let me delete others. So the total one. So similarly I have to, so remember this, you have to keep when the last one, that is the total one, and it's looking different from others definitely. So this needs some focus on the work, because if you miss any line, then that will create the problem during the plotting. So so if you have some more smart way to delete these lines, then you can also use, but this is my own way. So now for the second element, so these are the terms I have to delete, but carefully delete the lines, and only the total spin parameter and specific direction I have to use. So for the last one, last element, yes, Okay. Yes, completed. So this total 40 items have been, but these are not in the order. So let me sort this data sort that C. C. Yeah. So here it's from 1 to 40. So this last three lines, these are useful for us. So let me copy this and paste here in the last one, last three. So this is now okay. And we don't need this. We have to just use these seven columns, four earlier from XB file and three this additional one for spin vector. So copy this and paste it to this XSF file in the same place to this. Don't delete this to this total 40 items. Anyways, so now this is ready to use. So let me plot this by using X Christian. So here this is ready to use. So X Christian XSF star dot XSF. There is some issue. X, yeah, XSF. I have, yeah. So this is tool. What happened? Okay, so this is that structure. We are start working, and now let me modify some parameters. Atomic, not color, atomic. Let me display. Let me display atomic symbols. So these are that symbols. And second one is let me display these forces. So this will create the force lines. So these are that direction of spin vector or spin force. So just by clicking this in the display, when we click these forces, this line will occur. But the length is not looking presentable, so we cannot directly copy paste this to any manuscript. So we have to modify this. So let us go to modify and this force setting. So here in this force setting, we can manipulate these lines. So let me use this reduce this to 10 or 20. So let me update this. So this will reduce the size of this, and also let me change the background to look this better. So yeah, also some more different color. Yeah, it's okay. And some more parameters. So we can also reduce this to 6. Let me use. So now it's looking good. And this is that direction of spin that for the this zinc, and there is one is nitrogen in the opposite direction. So you can show this, and the length factor 1 point thickness of factor. So you can try the different parameters to set that different radius. So length factor is this, and vector color, you can change this vector color if you want to make more presentable. And also length factor cap here, that is let me use 1. So what will be change? So or 3, so that cap will look like this. So you can play with different parameters to set this arrow, but the direction of this is actually that's the direction of a spin. So this is okay. Now you can use this for this to present two spin direction. This is one direction and second one is in the second direction, and so this is the method to represent, and along with this you can show that table also, that spin and spin up and spin down, which is given in the result file, and that result will help you to give the answer of queries of that reverse, especially that what is that origin of the magnetic moment of that material. So what is that properties of that magnetic properties, why that magnetic properties occurs in a particular material. This is that because of that difference in the spinning of that electron, direction of spinning of that electron. So this okay. Thank you all, and try yourself. Happy learning.